Hello, welcome everyone in the room and those who have joined us from Rocket to my talk on assuring data quality at scale. I'll be covering a quick primer on what data quality is, why we are solving this for scale, what are the opportunities and challenges of doing that. I am Gayathri Thiyagarajan. I'm a senior engineering manager at Expedia Group. I've been working in data space for the last 3 years. I'm by no means an expert in data, but I've mainly been working on the streaming side using Kafka. In the 3 years, I've delivered a data product for capturing user interactions data as first-party stream. And then I've moved on to building platform capabilities such as managed Kafka as infrastructure, and more recently, a brand new capability for data observability across whole of EG data. Before that, I've delivered distributed system-based projects for high-profile clients. I'm a huge DDD evangelist and advocate, so obviously I've followed DataMesh patterns over the last 3 years. I also last year published a field story in a lean pub book on visual collaboration tools for how to use event-driven principles to model domain events for data capture. Naturally, as a DDD enthusiast, I feel duty-bound to put this warning up there. Today, when I'm talking about pipelines, I don't mean CI/CD pipeline, but rather data engineering pipelines. When I say metrics, it's not performance or system or application metrics, but rather profile metadata on raw data. I'll be covering that later. Checks is not code-style checks, but checks or constraints that you run on your data. And finally, when I say application, I do mean application wraps, sometimes in the context of stream processing. So let's start. Let's start to look at what data quality is, why it is important. Let's look at some of the issues that typically come up in production systems. So data is the lifeblood of any data-driven organization. What do we mean by data-driven organization? It's those orgs where data is woven into every part of the organization. It is key to deriving insights. It is important for coming up with business decisions. But a lot of organizations who are already data-driven or want to be data-driven don't have sufficient controls to assure them of consistent validity of the data or whether or not the data is arriving on time. For engineers, data scientists, and data analysts, good quality data means they don't have to get up in the middle of the night to tackle with P1 issues where pipelines, data engineering pipelines, are broken. And also they don't have to spend a lot of time cleansing and pre-processing the data. Therefore, a capability or multiple capabilities in some cases are needed in order to provide reliable and trustworthy data so that any organization or teams who are dependent on its success can make use of them. High-quality data is also important to perform insightful and dependable data analytics and thereby driving meaningful decisions. Consequently, a data quality tool is a fundamental building block in any organization for estimating how relevant are these decisions that they're making out of this data. On top of this, how do we do this at scale? In any medium or large-scale enterprises, we're shipping billions of events and hundreds of terabytes of data through streams, pipelines, and data lakes. Imagine running hundreds of distributed systems or microservices, but you don't have any operational metrics on how well they're performing or what their health is. That's a pretty scary thought, right? Then why would you run hundreds of data pipelines not knowing the quality of data that's flowing through them? So there is a need to do this centrally and at scale in order to provide the level of transparency and trust in order to provide the standardization in the metrics that are being calculated. There are several ways the data quality issues could manifest itself in production, which also means, fortunately or unfortunately, there are several metrics that you need to compute in order to detect them. Let's look at some real-world examples that I've gathered from support channels, so these are from production systems. Of course, I've obscured the field names and the dataset names here. Of course, these are just root causes. The consequence of these issues could be far more severe. So the pipelines could be broken or disrupted. There could be features not working on live site. Predictions could be incorrect, recommendations irrelevant. Sometimes it directly impacts customer experience. But at the same time, it's also important that we are able to differentiate legitimate data drifts, because the customer patterns have changed, the world has changed. We were all hit by pandemic last year, so obviously the patterns and how the customers interacted with our products and sites had changed. So we need to be able to differentiate that as well. All these data quality issues broadly fall under one of four buckets. The first one, incomplete data. So ETL pipelines and data processing applications, they normally expect a certain level of completeness for the data set to be useful for business purposes. Incomplete data will lead to pipelines dropping the data or throwing away the data because they're no longer useful, or stop if the amount of incomplete rows within a data set exceeds a certain threshold. What it leads to, in turn, is that they'll have to reprocess all that data, often at the scale of millions of rows, and expending a lot of compute and, of course, cost. In the case of streams, reprocessing data is a whole different challenge. But there are also certain domains like finance or tax, where even small amount of incomplete data is not acceptable. Incorrect data normally leads to two problems. One, where you recognize incorrect data or invalid data, and you're having to not use that data, like throw them away, which means you have a smaller subset of data to work with for your use cases. And more seriously, where you don't recognize invalid data and let it trickle through your data systems, and that could in turn lead to bad decisions. Obviously, you infer real-time using AI and ML models, where that means the predictions could be wrong, and you could have real site impact as well. For example, if you're using recommender systems based on this real-time data, that could get incorrect data to behave incorrectly. Late data could cause disruptions to pipelines. Two typical data processing patterns are one where you join multiple sources of data, and one late arriving pipeline could cause the whole thing to be stopped and waiting. Secondly, where you have a chain of pipelines where the output of one is feeding into the other, or there could be multiple downstream impacts where applications are waiting on the output of a single pipeline. In the case of streaming use case, of course, the SLAs and SLOs for those applications go out of the window, or it could also manifest as bad customer experience. For example, if you have a feature which shows recent searches that a customer has done, and you do this by reading live user interaction information, that search is no longer recent because the data is late arriving. This is when there is a difference between source and destination. Sometimes this is directly related to data loss in transit. In ETL pipelines and any transformation applications, the expectation is you have the same number of output events as that went in, unless the business logic dictates otherwise. So often the question is, how much data are we losing, and are we actually dropping data in between? So how do we measure? How do we measure data quality? And more importantly, how do we use these measures and metrics to detect issues? Data quality is often associated with fitness for use principles, so this also highlights that it's a subjective and context-dependent topic. It's also a multidimensional concept where a single aspect of data quality is defined by a dimension. By dimension, I mean accuracy, timeliness, consistency. So these are some of the data quality dimensions commonly used. There are others as well, validity, freshness, and you could go on. We'll cover some of those in a little bit more detail. Data quality metric, on the other hand, maps a dimension to a numerical value, and you can use that value to also assess if the dimension is fulfilled. For example, completeness is a loss function of number of events you would typically see within a time period. And the number of events is the metric, completeness is the data quality dimension. You could compute the data quality metrics at different aggregation levels or grains. For example, you could compute them at field or attribute level or column level, tuple or record or event level, and of course you can compute these metrics at the data set or stream level as well. So first dimension that we'll be seeing a little bit more detail is completeness. It generally is described as the breadth, depth, and scope of information that is contained within a data set. It also covers the condition that a data must exist in order to be considered complete. For example, if a partition has not arrived or is missing, it is still counted by this dimension. At the dataset level, of course, it takes into account the number of absent items, but at the field or column level, you could have this cover null values, or sometimes you could extend the calculation to include the default values as well, if the business case dictates that. So one formula to compute that is shown there. So obviously it's over a period of time. Next one is accuracy. This is one of the most important data quality dimension. This describes how close the data within an information system is to the real world that it's supposed to model. It's also most challenging to compute because there is no objective way by which you can measure how much the real world should contain. So normally you end up comparing this with another information system. So cross dataset correlation deviation is a very good example of how to compute this accuracy dimension. So one other example is if you expect about 100 orders within your data store or data lake, but only 90 arrive, so the difference is related to how accurate that data is. Next one is consistency. So this captures the violation of semantic rules on data items. And again, data items could be tuples at the relational table level or records or events. Referential integrity is a good example for consistency. But more importantly, this is where your domain knowledge is embedded. So the dimension directly relates to violation of those rules. So you could have multiple rules defined over a particular data item as well, and the consistency dimension calculated thus kind of accommodates all of those rules over a period of time. Next one is timeliness. So this describes how close is the data that you're using for a particular task at hand. It's closely related to, of course, currency, that is how up-to-date is your data, and volatility, how quickly does it go out of date. There are different definitions to this, and there's also a little bit of an overlap with another data quality dimension, which is the freshness. The other definition for timeliness is it's also the probability that an attribute is up to date for your use case. Normally, we use latency metrics or the inverse of latency metrics to calculate how timely your data is. This is one calculation, but not the one that involves latency. Right. I think it is important, we briefly touched or briefly mentioned subjectivity of data quality, but it's important to kind of highlight that a little bit more. There are subjective and objective characteristics to these data quality dimensions. So some of the dimensions that we saw, consistency, accuracy, completeness, timeliness, these are called hard dimensions. They are objectives, which means the interpretation of these values don't change based on the observer. And even though it requires some preceding domain knowledge, it's not subjective, or the evaluation of those dimensions are not subjective. Whereas soft dimensions are those where they are measured only through subjective evaluation of rules. For example, duplicate. Like, so if you want to determine if a particular row is a duplicate or set of rows or duplicates, the criteria for what defines as duplicate varies. That's better illustrated with this diagram, where it shows various actors on a particular data set. On the leftmost are the data producers. These could be internal or external applications, devices, third-party entities, and normally they produce against a particular data contract and at an expected frequency. And on the right are the consumers who use this data, so produced, for solving business problems. And again, they expect that the producers are generating against the contract and on time. Normally, consumers are on the receiving end of any data quality issues, so they tend to put in a lot of guardrails to protect their pipelines and applications. In the middle are the owners who are responsible for defining and upholding SLAs and SLOs on this data. And also we'll see a little bit more in detail that they are responsible for the quality of the data as well. In more cases, but not always, producers are also the owners of data, particularly if data producers or third-party applications. So this clearly, I hope, captures, because depending on who's observing and who are the stakeholders of this data and what they are using it for, the data quality checks that they want to run and what metrics they want to see and the dimensions, they could potentially change. So that shows the subjective nature of data quality. So moving on. Data architecture has evolved considerably over the past years, but over the past 3 years, there is one particular concept which has radically changed how organizations and enterprises particularly look and consider data. Data mesh. In simplistic terms, data mesh is all about well-defined boundaries around domains, which encapsulates applications, and also, more importantly, the data that are produced by these applications. So the data forms as part of the product. The product owners are also responsible, or the domain owners are also responsible for the quality of the data that they are producing. Along the way, data mesh has surfaced some of the challenges in the past data architectures, such as ability to surface, understand, discover, and use quality data. So for that, I think the whole data mesh architecture and pattern has come up with 3 different planes, as you can see here. The lowest layer is the data infrastructure plane, where you have the key infrastructure entities, such as Kafka topics or a NoSQL data store or a data lake table. And then there is the data product developer experience plane, where you have a higher order abstraction and provide tooling for the engineers in order to build data products over this infrastructure. And more importantly is the mesh supervision plane. So this is where you have centralized tooling capabilities that provide ability to be able to monitor, discover data, and also to govern data. The objective of data mesh, and I'm going to read off the slide, is to create a foundation for getting value from analytical data and historical facts at scale. So scale, in this case, is defined by changing data landscape. So we have streams to contend with on top of data warehouses, data lakes, data marts. Producer-consumer proliferation. Now you generate data, but there's so many different ways to consume, and there's so many interested parties to consume that data. Diversity in how we transform and process the said data. And finally, speed of response to change. So any data mesh implementation should address these 4 key principles: self-serve data platform, domain-oriented, decentralized data ownership and architecture, data as a product, we saw that, which also means that the ownership of data and quality of the data shifts significantly, and federated governance capabilities promoted by the supervision plane. So tying that back to the topic that we're discussing, obviously we covered the ownership of the data quality has shifted to the left, which means domain products and product owners are responsible and accountable for providing usable data and quality data. It advocates building platform capabilities for various different types of data sources, and we saw that proliferation of producers as well. Subjective specification of data quality. In order to achieve domain autonomy, each domain needs to be able to specify the rules that they want to run on their data set in order to be assured of the quality. And objective measures as well. So if I'm taking a data set, I need to be able to tell at a glance what are the key dimensions of that data, how complete is that, and tell that in an impartial and objective way. And also for governance purposes, of course. And finally, well-matured capabilities over unsupported and non-transparent solutions. So let's talk about how do we actually make this happen. Data quality is a huge space. It could cover a vast spectrum of things, particularly when you start to implement this centrally. You get thrown loads of things at you, like how about this, how about that? And some of the things that come up are quite obvious. Obviously, you'd expect a data quality capability to have a way of monitoring issues, measuring metrics, alerting and notification, of course. But there's also things like lineage, which tracks the life cycle of the data as it has kind of started its life from the beginning when it's produced, then it goes through streams, lands in data lakes, and then goes through attribute stores, gets consumed by an application. So lineage kind of tracks all the way through and kind of expresses that so that you can do root cause analysis. And once you have done root cause analysis, you need to be able to do some kind of a business process automation, triggers a JIRA issue against the producers. Of course, yeah, if you detect an issue, people go and ask, like, are you going to fix it? So auto remediation and fixing. Inline validation is like, yeah, why are you detecting once it's gotten into the streams or data lake? Why can't you just prevent it from getting into these data systems? So inline validation is more like pre-processing, if you like. But of course, it also touches, or it has some common aspects on other things like ML ops, which monitors model output, data drift, feature drift, concept drift, and loads of other things. They all have some common aspects, such as how do you detect issues, how do you gather metrics out of them, sending out alerting and notification, but there are clear boundaries. And when you set about implementing this at scale, it is very important that you have defined what the scope of your capability is. So let's just briefly look at what makes an effective data quality monitoring, because we'll be seeing some off-the-shelf offerings in a bit. First and foremost, of course, it needs to be able to run on different sources of data, NoSQL data stores or data lakes or Kafka streams or Pulsar streams or whatever the source of data. It needs to work on top of that. It needs to be near real time, or at least close to when the data is produced into these data systems. And more importantly, it needs to be able to send out alerts and notifications. It might sound very obvious, but there are a lot of offerings which don't provide this capability out of the box. And the engineers are having to actually monitor or stare at dashboards in order to pick out issues, which is not ideal. And of course, it'll be nice and important if you're doing this centrally to be able to measure these data quality dimensions and surface them in a common place. And finally, I think this is one of the most important thing that differentiates different offerings is how simplified, intuitive, and automated is the customer experience. when they interact with this capability. So cutting down on the number of configurations, at least the default behavior, is very important. There are some offerings differing in the levels of maturity outside in the market. Of course, there are quite a few startups who have started to look into this and build commercial products in data quality space. Soda.io, Great Expectations, that's PIP in the middle, Monte Carlo, but also Apache Griffin and AWS DQ, or open source library-based solutions. The startup products mainly work on batch data, at least at the time I read this talk. But they provide cloud-based services where you can monitor and visualize metrics and have various ways of configuring them, whereas the library-based solutions don't. But I think personally, for small to medium-sized enterprises, some of the buy options or the library solutions work. So you don't have to build centralized capability or even at scale. But large-scale enterprises with significant data assets, I think, require something far more sophisticated and mature. Of course, lack of centralized capability means a lot of these data product teams go and invent their own option. And I have personally come across a lot of homegrown options ranging from rudimentary solution to sophisticated anomaly detection-based tools. And some examples, good ones, use the pipelines directly use AWS DQ or Apache Griffin to specify constraints and collect metrics, or manual validations which are baked into the code, the data processing code, to offline checks being run on sample data, shoehorning that into an APM tool like Datadog, manually checking Tableau and BI, which is the most painful thing I've ever come across, and finally, bespoke homegrown solution, depending on the size of the data product team. If it's a very key business-critical data product, they go and invent something themselves, and they can afford to because the team is far bigger. Some of the challenges with these homegrown solutions are, of course, let's take the sophisticated option, for example. They are built, we talked about the subjective characteristics of data quality. So those tools are built to work with just one data product. So they don't scale for any other data product because their domain logic is pretty much embedded within the tool. And also, it's too much for a single team to be maintaining multiple products as well. So it quickly goes into an unsupportable mode. And also on the library-based solutions, there is always need to have common features such as alerting, monitoring, visualization, for which they expect integration with other tools in the space or go without. So what is the centralized platform approach? Of course, my team which built this are just getting into the MVP stage, so I'm kind of sharing the learning along the journey. But of course, there's plenty of things that we could cover. So the platform approach has 4 main decoupled stages, starting with ingestion, where you connect with the various data sources that we talked about. Profiling, which is all about computing metadata from raw data. Checking, which is the vital part here, running checks or constraints and rules on the metadata that we have computed. And finally, notify, that's the customer-facing aspect of this capability. All of this underpinned by a central configuration management, which would also provide self-service capabilities for allowing for customization or further customization of the tooling. So the first one. Obviously, we saw that DataMesh advocates that any centralized platform capability need to have support for different stacks, different data sources, and in our case, it's no different. Obviously, in a large enterprise, you always find a diverse set of technologies used for storing data. One team cannot be expected to provide or know all this in order to provide connectors for all of this. So we have used inner sourcing principles to get those teams involved in building the connectors as long as they generate data into a common contract, into the ingestion service, then all good. So they can go and build the connectors and contribute towards our platform. We also work in collaboration with some of the platform teams. We saw the data infrastructure plane. For example, streaming and data lake, they are one of the major sources of data. And we worked with them to automate how we ingest that data by plugging directly into their platform capabilities as well. As I mentioned, there are two major ways by which big data is these days kind of shipped. One is obviously in the form of streams, which is unbounded stream of events flowing through Kafka topics, and it facilitates near real-time consumption. Whereas data lakes, in our case, we use Hive Metastore, which is all about data at rest. So typical stream data, they are produced by internal product teams and power real-time use cases, such as personalization. We saw recent searches or placing ads or predicting customers' patterns and so on. And normally, Kafka streams are meant to ship high-volume events in a durable and scalable way. Whereas data lakes are a completely different beast. They store data in partitions, usually partitions or data time based. And you could have daily partitions or hourly partitions, but you could also have partitions based on one or more columns as well. This is so that you can have easier or faster retrieval for your applications. The main source is ETL jobs or pipelines, but also third-party data imports land into data lakes. And stream data are also landed into data lake for reporting and analytical purposes. Next stage is profiling. So this is foundational part of our DQ offering. We need to profile because checks run directly on raw data are not going to scale. Because you need to understand the structure of the data, for which you need to understand the domain, and you need to keep up with changes in that data structure as well. So profiling, as I mentioned earlier, is a process by which you gather metadata or calculate metrics on top of the raw data. Some examples of metrics are count of events, what's the missing or count of missing events or values in a column or attribute or rows, cardinality of an attribute, histograms, it could be category or range histograms, latency metrics, event size distribution, statistical distribution as well. You could have P95, P99, range, min, max, mean, median, interquartile range, quantiles, whatever you fancy. Variance, standard deviation, and so on. So you could calculate n number of metrics, and I would strongly recommend that you compute as many as you possibly can. These metrics also, as we saw, form the data quality dimensions or functions of these metrics. But you don't need to restrict yourself to just the ones that are required for computing data quality dimensions. Because a lot of these metrics on their own, if you're able to see the trends, as we'll see here, are also useful. So you don't need to tie them to a data quality dimension always. Sorry, that graph is not very clear. So that's the one that shows the light blue versus dark blue is the number of times or count that field is missing a value. And along the x-axis, all the fields within that stream. So at a glance, you can see how that is trending. It's also valuable when you're able to group based on a certain column so that you have a smaller subset of data on which you can run data quality checks. And again, this is one of the subjective way of running data quality checks because you know exactly what subset of data that you're using. For example, you might want to restrict the data to be grouped by partners or brands or whatever column or field is interesting to your particular use case. You could compute, of course, have like derived metrics out of this. You can calculate ratios of two metrics. And yes, it's endless what you can do with the metadata that you have computed. In our case, we actually leveraged the AWS DQ library to profile batch data instead of writing our own custom one. But in the absence of a solution for stream, we went ahead and calculated that ourselves. Exploratory data analysis is a very nice side effect of profiling. EDA, or exploratory data analysis, is a statistical approach of summarizing key characteristics of the data, and it's widely used by data scientists to kind of get a snapshot of what the data looks like over a period of time. So next one, checks. And at scale, the important approach to take is be able to offer multiple types of checks, not just restrict yourself to a single one. And some of the examples here, simple threshold where you define what the minimum and the maximum value is. Rule-based checks where you can have things like whether a value kind of is less than, greater than, between, or follows a particular pattern. Prediction-based checks, so we used encoder-based neural network model to detect anomalies, and accuracy checks where you compare source between a destination, particularly in an ETL pipeline. But of course, you need to be profiling that data across the same time window in order to provide that comparison. Few things to note here is, of course, with these different type of checks, we're not offering one size that fits everybody, because the needs, as we have seen, as you have to implement more and more subjective checks, it's important to have these different types of running these constraints. And also, don't think anomaly detection is going to solve all the problems. At scale, it comes with its own challenges. In our case, we had one model that was trained on dataset field metric level grain. So obviously, we lost a bit of accuracy on how well the predictions were. So we kind of resorted to doing this at dataset level, and that's an expensive activity. So it's good to kind of restrict yourself to a set of metrics that are likely to change in terms of trends, taking into account seasonality. For example, count of events. It's very difficult to pinpoint that within a threshold. It could change wildly, and there's a lot of ambiguity on what that pattern should be. Whereas where a column should contain like 3 values or what those values should be, you don't want to expend an anomaly detection model over that. So tap into the domain knowledge from the domain owners as much as possible in order to identify what type of checks best suit them. And one good thing that we have implemented was dogfood our own outputs. So all of these, when I said decoupled, the output from every single step was actually fed into a Kafka stream. So we could, in theory, profile our own data, profile the check results, and make sure that they were working as expected. As I said, this is the customer-facing aspect of our capability, so it's very important that you're proactively sending notifications through Slack, email, or messages. Nice thing is you could connect to PagerDuty or any other alerting mechanism that you're using within your organization for effective response to data quality issues. And you could go one step further, is collect feedback from the customers on how accurate were these alerts, how useful were they, so that you're kind of using that to train your models as you use labeled data sets to train your models to improve the accuracy further. Right, Okay, mindful of time. So doing this at scale obviously creates transparency. Everybody knows there is a standard way of computing these dimensions across all data sets, and there is trust as well. It obviously rewards cleaner data practices, and you're able to surface and promote these data sets in any data discovery tools that you might have. Of course, building an extendable and inner-sourceable platform. You could bring in connectors for data sources that your team uses. And of course, you could plug in any other prediction or forecast-based models into it as well. And finally, we touched on this, reusable metadata, the profile information. We saw EDA, the exploratory data analysis, is one nice side effect. Another one is you could use that for data reliability purposes, which identifies which part of the platform is broken, why, and so on. And of course, you could also use some of these basic functionalities or reuse them for doing model output monitoring, if you fancy. Of course, doing anything at scale comes with challenge. First one is achieving reliability and trust. In this case, I'm not talking about the data itself, but about the tool or the capability. As something that is promoting transparency and trust, it needs to be trusted first and foremost. So sending out false alerts or false positives is not acceptable. So you need to have strong foundations in order to be able to build that trust over time. Of course, engineering for different types of ingestion was another challenge that my team faced, particularly streams and data lakes and the different combinations of how data could be partitioned in data lakes. That was eye-opening, and building that at scale and coming up with a common template by which we can onboard those data sets was a big challenge. Anomaly detection, I think we covered that in detail. I think it's the grain to which you want to do anomaly detection and keeping those models trained continuously so that the predictions are relevant and up to date is a challenge. And also, given that we needed at least a month or 2 months of profile metrics to train the models, we needed a fallback option, because we can't say like, oh, you have onboarded, come back in 2 months, we will alert you on data quality issues. That wasn't going to fly. So subjective and objective measures, being able to have a centralized way of computing the data quality dimensions, but also providing a self-serve platform that would allow the domain owners or the product owners to specify what rules they want to run on their data and be able to see their alerts in a customized format is another challenge. So the final one is the customization, not just on the alerts, the thresholds. You need to be able to define a subset of data. We saw the grouping and the segmentation of the data which interests you, your particular domain, and capturing all of that as part of the platform and building that 4 stages of running checks on each of these is a critical part of offering this as a central capability. So, concluding, data quality is important. I hope I made a good job of driving that point home because it promotes trust, transparency, and cleaner data practices within the org. Of course, you only have a certain amount of control with the data that's coming from outside, but this provides a certain amount of protection against that. Centralized data quality capability with proactive notification and alerting at the bare minimum is essential. But also to make it more mature capability, you need self-service. You need automation. The customers only need to do customizations only if they absolutely need to. Out of the box, the default behavior should be very simple. And finally, awareness of domain challenges, but also build the tooling in such a way that it doesn't need to understand the domain is very important, and it's quite a challenge as well, because you have so many diverse data flowing through your organization that it's absolutely not possible for you to understand each domain and build the capability for it. So these are some of the references to what we saw earlier. The first paper is a really good read on data quality. Then, of course, we have covered the DataMesh principles, mainly from the blogs written by Zhamak on Martin Fowler's site, and links to some of the data quality offerings we saw earlier. I didn't mention LinkedIn's Third Eye, which is an open source offering, which is far more similar to the anomaly detection tools that we saw. Mainly used for business KPI monitoring, but you could use that for doing data quality checks as well. Thank you. Happy to answer any questions, or I'm around after the talk here. Sorry.
Yeah, so I work on a team as a software engineer, and I work with people like analysts on my team that analyze our data. We sort of have a separation between the people that sort of own the data, which is us, and the experts that know what does it mean to have quality data. And currently, the way that they sort of help define the set of validations that we want to be able to do on this data in a domain-specific way. And then we try to implement that. And recently, we've been trying to give them more power to directly put their validations on this data. They aren't necessarily programmers. They can write SQL, but we don't want them to be writing, or they don't want to be writing code.
Of course.
What are some useful patterns we can use when, I guess, the people that are domain experts on the data and they know how it should look like, and how can they give their feedback in an actionable way on the data quality and what it should look like?
Yeah, this goes back to the different actors that we saw. If I didn't misunderstand how we were describing your situation, it seems like there is a consumer group for your data who know exactly what kind of checks they want to run because they're consuming the data analysts. And you as data producers also have like an invisible responsibility of upholding those, but it doesn't necessarily have to coincide at the same time. And in terms of patterns, of course, it is about actually capturing those rules and surfacing them in a transparent way. The self-service capability, I think that is one of the key part here, is you don't need to know a particular language or a way of running those checks. SQL query is important, but it's not always easy to read and change. So yes, the self-service capabilities kind of help promote that, where you have product owners who are not exactly technical can also define these rules, and you have a central way of accessing what rules were run, and you can also provide version control over them.
The other problem we run into sometimes is the specifications on what the data should look like often produce too many, I guess, validation errors, and so obviously if you see spikes of errors, maybe it's something in our process, but sometimes it's just data that we're ingesting happens to be wrong a certain percentage of the time, and they care about some of these errors more than others, but we're never going to get it perfect.
Yeah.
When working with things like that, I guess, what are some ways to, I guess, help define, like, I guess that's the subjective part of data quality.
Yeah, so subjective part is where you're defining these rules. So something that we haven't personally implemented, but some of the cloud offerings that I mentioned, so did IO, Great Expectations, what they provide is ability to be able to configure alerts depending on the severity of the issues. Sometimes for example, a producer has gone bonkers and for that particular day or week you're going to receive invalid data. So you need to be able to mute or be able to reconfigure how severe those alerts or whether or not you want the engineers to be woken up in the middle of the night about it, something that is completely on fire, or there is very little you can do about it. So there are like a range of issues that could come up, and being able to configure that at the alerting or notification level, because you don't want to suppress the data getting profiled or the checks being run in case situations change and you want to be alerted. You still need to be able to do that. The configuration kind of lies on the notification side, and that's one of the customizations that you could have. Right. Time's up. Thanks everyone. Thanks for your time.